Now I'm going to have you do a quick thing. So I'd like you to flip this paper over. So we're looking at these continuous parent functions. I would like you to flip the paper over, and I just would like you to go through and do some of these examples. So the first one I'd like you to do is I'd like you to do example 1. So I'd like you to stop your video, and then I would like you to make a graph of the function for example number 1. Okay? So pause the video, make a graph of example number 1, and do questions A through D. Okay, so this is your graph that you should have created. It should have been a function. It looks like an absolute value, which is always a v. And now it wanted you to figure out the slope from the left, okay? This means right here, the derivative. But it also is the derivative as x approaches 3 from the left. So think about this. We're starting at 3, and we're approaching from the left. But notice it's a straight line. The straight line has its same slope no matter where I am on this line. Okay, so what is the slope from the left? The slope is -1. Derivative is the instantaneous slope right here. So coming in from the right, the instantaneous slope is going to be -1 because we're following this line all the way down. Now take a look at the next one. It's at finding the derivative again. The derivative is the instantaneous slope. So you come in from the right side. Now notice, the right side's a little different line, but it is a line. The slope on a line is always the same. So this one goes down 1 and back 1, or you can think of it as up and over 1. This one has a slope that is +1. Okay? Now, the question is it continuous at 3? Well, from the left, remember, the left limit is equal to 3. The right limit is equal to 3. And the value, 0. The value from the right is 0. And the value at r of 3 is 0. So is this continuous? Yes. Now, is it differentiable? Okay, because the derivative from the left, okay, so the f prime of x from the left equals -1, and the f prime of x from the right is +1, this would now be a no. So this is a continuous function because there is no gap space or things like that, but it is not differentiable because the derivative from the left does not equal the derivative from the right. So now I'd like you to go through, I'd like you to pause the video, and I would like you to do example number 2. Okay? So go ahead and do example number 2. And that is, I will say, if it's hard to read, it is x to the 2/3. And it is one of those parent functions we saw on the other side. And so it goes like this. It kind of looks like a wing of a bird. Okay? So it looks like the wing of a bird. So it says, describe the derivative as x approaches 0 from the left and from the right. Well, let's talk about from the left. From the left, notice that if I draw tangent lines, all of these derivatives are negative. Okay? So from the left, the derivative is a negative value. Now look at it from the right. If I come in from the right, and let me use a blue line, notice all of these tangent lines are positive. Okay? So the derivative is the slope of the line at those points. So we look at those tangent lines and we notice that it's negative from the left and it's positive from the right. So if I was to say to you, is this differentiable? You would have to say this is not differentiable. Okay? Now, they do give us a little hint in the next one. They say, well, what if the derivative is this? And this is actually the derivative. So using that formula, what is the value of the derivative when x is 0? Well, when we plug 0 into this, you get 2 over 0, so it is undefined. Okay? Once you know the derivative, if it is undefined, you know that it is not going to be differentiable at that spot. Okay? So any undefined derivatives are not differentiable. So now, let's take a look at the last one. Stop your video and go ahead and answer questions A and B, and then start the video up again. So, the graph for part A, it says, is the cube root of x. Okay? So we have the cube root of x. Now, if you look back here, the cube root, oh, it's not one of our parent functions. Interesting. Okay, so let's talk about the cube root. So let's take out our calculators and let's graph that just quickly. So let's clear that, and we'll clear this, and let's do the second. Ooh, it's cube root, right? Okay, so I'm going to do this a different way. I'm going to clear this. I'm going to do x to the, and I'm going to use 1/3 power, because if you remember, you can convert roots, cube roots, to fractions, and I'm going to graph it. And there is our graph in the standard window. So it goes like this. It gets really close, then it goes up, and then it goes something like that. So this is the cube root function. Okay? Now, it says, describe the derivative if x approaches 0 from the left. Well, from the left, you'll see that it's positive. And from the right, you'll also see that it's positive. Okay? So, we have something weird that's kind of going on. They're both the same. But what happens when we put it into, this is actually the derivative of that function. Okay, this little thing right here. So it says put 0 into that. We have 1 over 3 cube root of 0 squared. You'll notice that this too is undefined. Okay, so there is an interesting situation that occurs when something like this happens. Okay, what I want to let you know is I'm going to introduce a word for you. This is called concave up. Notice that this opens up. The curve opens up in this direction. This one is called concave down. Notice that the curve opens down this way. Whenever there is something, whenever it changes from concave up to concave down at a point, there's something here called a vertical tangent. These vertical tangents always have an undefined slope. Okay, because remember, if you take the slope of that line, it's the rise is whatever number, and it's divided by 0. So it's always going to be a rise divided by 0. So whenever you see a graph that does this, there is, at 0, it is not going to be differentiable. So this is not differentiable because it has a vertical tangent which has a slope of 0. So the same thing would probably hold true for this arctangent graph over here. At 0, it would be undefined. Okay? So, to recap, okay, let's go back to our notebooks. To recap, when are things differentiable? So when is a graph differentiable? Or actually, let's do not differentiable. Okay, what does that look like? Well, there are three situations where that is the case. The first one is when the derivative from the left does not equal the derivative from the right. Okay? Like in this case, this is called a point. So whenever you see a point on the graph, you know that that is not going to be differentiable. Okay? The second case is very similar. It looks like this. Two graphs that kind of curve in like that. Notice again, the derivative from the left does not equal the derivative from the right. Please remember the derivative is the slope of the line. This is called a cusp. And the final place where things are not differentiable is number 3. It's where the graph goes like this, turns like this, and goes like that. Where things go from concave up to concave down. Those places have something called a vertical tangent. Okay? So these are the three situations. When you see those in a graph, you know that they are not differentiable in those spots. Okay? So I hope that helps you out, and I hope this will help us complete what we are going to do tomorrow. So good luck, have a great evening, and I will see you soon.